Okay. Is it recording? I think it's recording, so sorry for the mess. So I just want to take the opportunity to thank David Gossett for the great job for organizing that seminar for the past 2 years. And today we have the pleasure to have Levent Tuncel for giving the talk. So Levent graduated from Cornell and has been a professor in our department for over 20 years. And he works in various aspects in optimization and research, operations research. And today he's going to talk about a notion of total dual integrity for convex, semidefinite, and extended formulations. Levent.
Thank you very much, Jane. Thank you very much, everyone, for showing up. I would like to start the talk by making a few remarks. So this is about total dual integrality, and it's joint work with Marcel de Carli Silva, who was a PhD student here in our department. And one of the things that we are blessed with in the Department of CNO is brilliant PhD students, brilliant graduate students. I've been very fortunate to have only brilliant PhD students. That's awesome. And in these difficult times, I think it's important that, you know, we share some feelings with our family members. So in my academic family, the CNO department, I would like to share with all of you that this moment, being able to give this talk on a subject like total dual integrality in a medium like Tutte Colloquia is incredibly special to me. When I first started learning about total dual integrality, approximately about 30 years ago in a graduate course, indeed, my first reaction was, nice, very good. And, you know, shortly after that, I, you know, started thinking about some related things. And if somebody told me 30 years ago that I would have this opportunity, I would say, oh, that's perfect. That's all I need out of my life. So I just wanted to share that this is indeed an incredibly happy moment for me. So you might say, why total dual integrality makes this special, among other things? Well, total dual integrality was born here. But by here, I mean the Department of Combinatorics and Optimization. And at the beginning part of our cookie time, one of the colleagues suggested that perhaps I should consider calling on the colleagues attending and students attending and asking them questions. So I don't like to do that when I'm not sure about the answers. So, but I will make a conjecture. I will make a conjecture that the academic mathematicians who made contributions to the theory of total dual integrality, by far the largest group who made the deepest contributions are connected to the CNO department. So I would like you to think about that, and we will have an extensive discussion about this during the beer time. All right. So so just to we'll get there. All right. So let me just explain some basic definitions, so that if you haven't seen the definition of total dual integrality, then at least we are on the same page. A vector in Rn is integral if each of its components is an integer. All right. And the rational system of linear inequalities, so by that I mean I have a matrix that's m by n, where every entry is a rational number, and a column vector B with m entries that also has all rational entries, then the system of linear inequalities is called totally dual integral if for every integral vector that you pick that will make up your objective function, the linear programming problem due to maximizing Cx subject to Ax less than or equal to B has an integral optimal solution whenever it has one. So that's the definition of total dual integrality. And it's one of the most powerful ways that we can detect when a linear programming relaxation or a polyhedral relaxation of a combinatorial problem is exact. It has other consequences, but that's just one. So in this case, the polyhedron determined by these inequalities is integral. For instance, if it is a polytope, if it is bounded, then every extreme point is an integral vector. And in general, each non-empty face of that polyhedron has an integral vector in it. All right. So this last result was proven by Edmonds and Giles in late 1970s. And as many of you know, at the time, Jack Edmonds was a faculty member in the department, and Giles obtained his PhD from our department. But of course, things don't stop there. And if you look at the results related to total dual integrality, for instance, many of you are familiar with Bill's book, and each of those bills have done very foundational contributions to total dual integrality. So Bill Cook, Bill Cunningham, Bill Puyblank, also with students and co-authors, and Alexander, Lex, Bill, Scriber. So, and of course, I mean, it doesn't end there in terms of the connections to the department. As I said, Jim Gillen has at least one very nice theorem about total dual integrality. I'm sure you might be sitting on many others. Bertrand Guérin has many related results and theorems. And as recently as 2 days ago, I had a meeting with Bertrand Guérin and Zauer, and TDI-ness came up. So it's really a very special subject for our department. Okay, so here is the theorem of Edmonds and Giles. You have rational data describing A and B, and if for every objective function that's integral, the optimal objective value of your LP is either is an integer, or the LP is unbounded or infeasible, then the underlying polyhedron is integral. All right. So in this talk, actually, we are going to start from an older theorem due to Hoffman. So before Edmonds and Giles, Hoffman had a version of this theorem for polytopes. So it's essentially the same statement, but you assume that the polyhedral set you're talking about is bounded. All right. So one of the very attractive and easy to understand consequences of total dual integrality is the following. When we have a TDI system, AX less or equal to B, we can do the following. We can consider the integer programming problem where we want to maximize that objective function subject to the constraints describing our polyhedron and the additional non-convex requirement that our variable vector is integral. Okay, and then once we remove this integrality condition, then we have a relaxation. This is a linear programming problem. And since we remove the constraint and we are maximizing, the objective value can only get higher. Okay, and I am assuming that the primal problem is feasible. And then we have got linear programming duality. So I'm assuming that this problem and its dual are feasible. Therefore, I have strong duality in this case. And we have got this chain. So I have a hard combinatorial optimization problem, and I have related that problem to a linear programming relaxation and its dual. And you see in this setup, there are a lot of possibilities for deriving solution methods, proving theorems, and so on. Okay, But with TDI-ness, things don't quite end there. There is something more. So when you look at that dual problem, suppose that I want to restrict my variables in the duals to be integer valued as well. So when I do that, I know that this value is finite, this problem is feasible. So I am making the feasible region potentially smaller over here because I have added an additional constraint. The objective function is the same. Therefore, the objective value can only go up. It may become infeasible, but in that case, the infimum over an empty set is plus infinity, and this inequality is still valid. So I hope this is clear. All my screens are functioning okay. All right. So then what happens? Well, if my system Ax less than or equal to b is totally dual integral, then equality holds throughout this chain. But notice that the primal problem, when restricted to integers, is a combinatorial optimization problem. But so does the dual. It corresponds to a combinatorial optimization problem. So is the dual. So if we have equality throughout, we actually have a combinatorial min-max theorem. We are saying that maximum of weights over some combinatorial structure is equal to the minimum of some other weights that come from here of some other combinatorial structure that's defined by the same data ABC. And this is extremely powerful. Of course, once you have min-max relations, you could also start thinking about deriving combinatorial primal dual algorithms, proving other structural results, and so on. Any questions about this beautiful classical setup? All right. All right, so let us think about how to generalize this to semi-definite programming problems. So semi-definite programming problems are a very powerful generalizations. They are very powerful generalizations of linear programming problems. So whatever we can do with linear programming problems in terms of approximation to difficult sets, we can do at least as well with semi-definite programming problems. Okay, so again, as you can imagine, I'm going to use a duality theorem, so I need a suitable constraint qualification. But now I want to look at the problems that are semi-definite optimization problems. So this curly inequality refers to the partial order in the space of symmetric matrices induced by the positive semi-definite cone. So when I write some symmetric matrix, curly greater or equal to some other symmetric matrix, what I mean is that this matrix minus that matrix is positive semi-definite. So the positive semi-definite matrices in the space of symmetric matrices is a pointed closed convex cone. Every such cone induces a partial order in its space. And this is the partial order called Lerner order, if you have heard about it. So here I've got some linear inequalities. I have a matrix variable, an n by n symmetric matrix required to be positive semi-definite. And we are going to need some kind of non-convex constraint that will help us model some difficult problems. That will be the analog of requiring a vector to be integer valued or integral. Okay, so our focus will be on combinatorial optimization. So I'm just focused on sets, finite sets in Rn. So I'm going to embed my finite set as a collection of 0, 1 vectors. And to represent those 0, 1 vectors, I'm going to embed my matrix as an n plus 1 by n plus 1 matrix. And the initial entry is, this is the one I'm going to call 0th column and 0th row. So this entry, 0, 0 entry will be 1. And then I have a size n vector x, it's a column vector, and it's transposed over here. So my matrix is symmetric. And then I'm going to have an n by n symmetric matrix x. So my variable will be x hat in my semi-definite program, and I'm going to require it to be of this form. So only thing I'm really requiring is that 0, 0 entry be 1. So having this setup, it's quite easy to enforce 0, 1-ness of the small vector x. I'll write the linear constraint that the diagonal of this n by n matrix x is equal to this vector. Okay. And then I'm going to require later that this matrix x hat is rank 1. What that will force is that the ith entry of this small x is equal to its square. Well, there are only two solutions to that quadratic equation. It will imply that every entry of this vector x is either 0 or 1. Okay, so that will be the way that we're going to embed combinatorial optimization problems as STPs with some non-convex constraint. And once I have such a setup, I can remove that non-convex constraint and end up with a semi-definite optimization problem, a tractable problem. All right. And then under a suitable constraint qualification, for instance, assuming that, say this problem has a Slater point and the objective function objective function of the dual problem is bounded from below, or that they both have Slater points or something weaker, we can guarantee strong duality and equality between these two values. And depending on how much we assume, you can also obtain attainment. So for instance, if I assume that both problems here, both STPs have Slater points, then both of these suprema and infima are attained, and they're exactly the same. Okay, so then again, we have the kind of setup that we saw in the polyhedral approach to integer programming. And in this case, we're using semi-definite programming in place of linear programming problems. And I can tell you there are thousands of papers, probably at least 1,000, that use a setup like this, that embed a hard combinatorial optimization problem, write an STP relaxation for it, write down its dual, and use all of these three to prove theorems, derive algorithms, or generate even software. So this part is common. What's missing, what was missing before this work, was this last part. So one needs a natural constraint for integrality in the dual, so that when we have an analogous version of total dual integrality for convex optimization problems that are nonlinear, we can still benefit from the chain of inequalities becoming equations, derive min-max theorems, derive algorithms, and so on. So, but still, the chain is there. You can impose any non-convex constraint you want. This inequality will be true. The chain of inequalities will still be true. But the trouble with introducing non-convex constraints here willy-nilly, you can end up with meaningless dual problems over here that will not give you useful results. Okay, so I'll quickly, instead of keeping the mystery, I'll quickly tell you what works. So what works is that we look at the dual slack and the dual STP, and the integrality condition is that we will say that S is integral if that dual slack can be written as a sum of rank 1 matrices. And I also want each of those matrices, S1 through S sub capital N, to have the structure that we talked about over here on the primal variable. This entry in the dual variable, I want it to be 1. And for the primal variable, we had this relation that the zeroth column of this matrix is same as the diagonal of this n by n matrix. So this was the one when we additionally enforced rank 1 constraint. forces the variable vector x to be 0, 1 valued. Now, when you take the dual of an STP that has this kind of constraints in the dual, the kind of condition you get is this. So it's an analogous condition. The only change will be that in the dual variable, you're going to have a -1 here and -1 here because of the definition of the dual. And in fact, this is same as the primal condition. So actually, this definition is primal dual symmetric. One of the ways that we embed difficult problems as STPs with a non-convex constraint is simply to enforce that the positive semi-definite matrix variable is rank 1. And if you have an additional condition that says that summation of the 0, 0 entry of those matrices is 1, then in that case, of course, in that sum of rank 1 matrices, you may only have one matrix. So it is a special case of the dual condition that I mentioned, but actually they are symmetric. You can write the integrality condition both in the primal and the dual as given by this definition, except that in the primal you're going to have a minus sign here, and in the dual you have a plus sign. All right, any questions? So we have a notion of integrality for the dual problem. It is saying that the dual slack must be summation of rank 1 matrices, where each of the rank 1 matrices are of this form. Any questions? All right. So maybe at this point I should draw a little chart because things are possibly gonna get messy. So just to make sure that we are gonna be on the same page. So what we have is we have some finite set that might be for a given graph, the incidence vectors of stable sets. For a given graph, it could be the incidence vectors of matchings. So any kind of combinatorial object that you want, or incidence vectors of Hamiltonian cycles. And in general, you have a polyhedral relaxation of the convex hull of such points. So here we're looking at it more generally. So what we have is a convex relaxation of the convex hull of those guys. That's not necessarily a polytope. All right, and this is something that really lives in. So this is something that lives in Rm. But then we're trying to write an STP relaxation for it. So then what we are doing is we are going up to a space of n+1 by n+1 matrices. So this is the space of n+1 by n+1 matrices. And in this space, we are having some other set that is high dimensional, and so that its projection onto the small x variables is precisely this red set. So what does this indicate? Well, for instance, if you have a total dual integrality that you're interested in, you're going to look at linear functions given by some, say C vector for various C vectors. And then indeed, you will need to lift this C function up to something else. So there will be a linear transformation that will lift that C vector to a corresponding matrix so that you have the corresponding objective function in your in the space of symmetric matrices so that you can state your STP. So there are really, in addition to the dual spaces that are in the natural domain of total dual integrality, you also have this higher dimensional space that is in the space of n+1 by n+1 matrices. Okay, So to generalize total dual integrality, we are going to start from the bottom. So we're going to focus on this convex set over here and its properties. Okay, so here's a very elementary and nice theorem. It's not hard to prove. If you have any compact convex set, then you can write that compact convex set as intersection of half spaces that are given by support function of your convex set, only described for integral vectors. So what you do is you basically show it for the rational vectors, and then you scale. So a support function is given a vector in Rn, it returns the optimal objective value of maximizing Wx over your set script C. So every compact convex set admits such a nice description in terms of integral vectors. Okay, this is nice. So let us denote by C sub I the convex hull of the integral vectors in our convex set. Wonderful. And using a little bit from integer programming theory, what I would like to call Gomori-Kavatal theory. And as I mentioned, Kavatal, there's another mathematician who obtained his PhD from our combinatorics and optimization department using a result based on Gomori-Kavatal theory. We can actually conclude the following generalization of Huffman's theorem. That's the theorem from 1974. And that is that if you have a non-empty convex compact set, that set is exactly equal to the convex hull of integral vectors in it, if and only if the support function of that convex set is integer valued for every integral vector. So it's really a beautiful and simple result. And then if you have taken maybe CO650 or 652 or something related, you have seen a theorem that is similar to this for polyhedra, characterizing when a polyhedron is equal to the convex hull of integer points, integral vectors in it. And then you have characterizations like every non-empty face of your polyhedron contains an integral point. Exactly the same statement holds here. And when I say this, I mean the following are equivalent. These are equivalent characterizations. And then if you pick any vector in Rn and you look at the set of optimal solutions of this linear program, or in general, in our case, convex program, it's attained by an integral vector, and every rational supporting hyperplane for the convex set contains integral points. And I want to throw in something more convex analysis, like to tell you that you can actually make quite weird statements that involve the polar of the set, where the statement looks quite, the left-hand side looks quite weird and continuous, and the condition tells you that it has to be an integer. So I'm not gonna bore you too much with it, but since we're in the domain of convex sets, you can actually have such statements that are equivalent. So one of the byproducts of this work is I was trying to explain. So I should go back to the Mickey Mouse picture that I made. Go back to this picture just to remind you. So we are talking about total dual integrality of some formulation that's in the lifted space, a higher dimensional space than where our finite set lives. And on the space where our finite set lives, we have a corresponding convex relaxation of the convex hull. So there, the objective functions are just vectors in Rn. But since the set that we are interested in is a projection of a higher dimensional set, up here, we do not care about every possible objective function. We only care about those objective functions that correspond to objective functions from here. So we have a linear map that lifts those relevant objective functions. Okay, so for instance, if going up here, I only increase the dimension by 1, I added a new variable xn plus 1, then in that case, I would only be looking at the vectors where, say, the last component is 0 and plus 1 component is 0. And that would model every n vector here. Great, so that's where we are. So that's why that kind of a map is relevant. Then our definition of TDI-ness for these semi-definite optimization problems and related convex optimization problems is that for every integral vector in the natural domain of your combinatorial problem, the semi-definite programming dual to this primal SDP has integral optimal solution whenever it has an optimal solution at all. So notice that in this case, integral means that the dual slack can be written as sum of rank 1 matrices. All right. So so now here's a theorem. Then if we have an SDP that's given by these linear inequalities and positive semi-definiteness constraint in our matrix variable, that SDP we call TDI through a linear map, like I described. So that's the assumption. I'm assuming that my SDP is totally dual integral with respect to the new definition. And I just want to make sure that its projection, when I project my feasible region of my SDP to the space Rn, it is the right integer programming formulation. That's what the second assumption is. It looks like it's a lot of notations, but all it says is that that is the right set. And then we assume that B is integral, and this is just like the polyhedral TDI-ness. We assume that C is compact. That's like the Huffman's theorem version. And C hat has a positive definite matrix. So that's the constraint qualification for the SDP relaxation. It has a Slater point. Okay. Then our convex formulation is exact. So this is the analog of Edmonds-Giles theorem, and it's the generalization because it includes Edmonds-Giles theorem as a special case when you're dealing with polytopes. All right, there's a more technical version, but I'm not going to be able to make my time, so I'm gonna simply tell you that under the assumptions of the previous theorem that I mentioned, we actually get that equality holds throughout when our system is TDI, and we get the corresponding chain of equations with the non-convex primal restriction of the SDP having the same optimal objective value as non-convex restriction of the dual SDP, therefore giving a min-max theorem that are combinatorial. That's combinatorial from both primal and dual sides. Okay, so let me tell you a quick application. As I mentioned, for bounded polyhedra for polytopes, it generalizes Edmonds-Giles theory. So any TDI-ness result from polytopes is included as a very special case of this theory that I just presented. But let me tell you some very nice example, very nice application of this theory. So for every graph, the following are equivalent. Graph is perfect, and its complement is perfect. This is a theorem of Lowas from 1972. And the stable set polytope of the graph is same as its clique polytope. So the clique polytope is the polytope defined by constraints where you require your x to be non-negative. And for every clique in your graph G, you write the linear constraint that says you may take at most one element, at most one node from that clique in your stable set. So this polytope is intractable in general. It's NP hard to optimize over this polytope in general, not for perfect graphs. So another result before our result is that when you look at the system of inequalities that describes a polytope, and that polytope is TDI, so the inequalities that are defining this clique polytope is TDI for a given graph, if and only if your graph is perfect. So this is very nice. And Lowas has a beautiful seminal paper from 1979 where he uses semi-definite optimization to solve an open problem in communication theory about Shannon capacity of graphs, more precisely Shannon capacity of the 5 cycle. And there he defines what's called now a Lowas theta body. So another equivalence here in this theorem is that a graph is perfect if and only if the Lowas theta body is a polytope. So otherwise, if the graph is not perfect, this convex set has some nonlinear pieces on its boundary. All right. There are other versions of the theta body due to Lex Schreiber called TH prime that defines the invariant graph invariant called theta prime, where in the STP relaxation you require the variables that are not restricted to be non-negative. So it provides a tighter relaxation of the stable set polytope, but the same conclusion applies to that convex set as well. That nonlinear convex set in general is a polytope if and only if the graph is perfect, and this set TH primed is in general a proper subset of the Lowas theta body. And there's another one, again, going back to the work of Schreiber and more recently Mario Szegedi. This is TH plus, that's a relaxation of the theta body. So all three of these have semi-definite programming representations. This is in the middle. This is in general smaller than the theta body. This is a relaxation of the theta body. But all of these sets in general having nonlinear boundaries become polytopes if and only if the graph is perfect. So these theorems existed before our work, and these theorems are about the convex set that lives in Rn, when n is the number of vertices of this graph, number of nodes of this graph. But as I said, these sets also admit semi-definite programming relaxations in the higher dimensional space, whose projections back onto Rn are exactly these guys. So we can prove in our theory, the new TDI-ness theory, that a graph is perfect if and only if that STP representation that Lowas proposed in 1979 is totally dual integral with respect to our definition. Moreover, our definition is robust in the sense that when we apply our definition to these different variants of the theta body in their corresponding lifted STPs, they are TDI if and only if the graph is perfect. So let me try to conclude quickly. So what is this? What is this theory? Well, TDI-ness, total dual integrality, is a theorem proving machine. Given any combinatorial optimization problem, there exists a set of linear inequalities that will formulate the convex hull of that combinatorial vectors, such that the system you formulated is TDI. So you can search for any combinatorial problem for that linear system of inequalities. In this new theory, the same holds for any combinatorial problem that has a finite embedding as a 0-1 integer programming problem, that there exists an STP that is TDI according to our definition. So when you show that, when you find for your hard combinatorial problem that STP relaxation that becomes TDI, so that it's no longer a relaxation, you actually have the chain of inequalities on 4 optimization problems becoming equalities, and you have immediate min-max. You have an immediate combinatorial min-max theorem that are derived through a primal dual pair of STPs. So you can prove TDI-ness theorems and their combinatorial consequences like min-max theorems, but now you can do it based on STPs. And once you have that, then you can think about even designing new combinatorial primal dual algorithms. All right. And what else remains? Well, I would like to obtain a primal dual symmetric integrality condition for STPs that applies to arbitrary integer linear programs, not just 0-1 integer programming problems. And there are some difficulties. The result from the Gomori-Kavatal theory does not generalize to that setting, the kind of result that we need, and there are other drawbacks, there are other difficulties. Another big thing that one can do is that the STP relaxation framework that I discussed is universal in the sense that almost any non-convex problem can be embedded like that STP with a rank condition. And since we have got the sequence of those 3 problems already, to find the restricted dual for continuous non-convex problems would be an awesome new result. So extending this theory to non-convex sets that are coming from continuous problems, where the feasible region is continuous. It's not just, say, union of points, like in integer programming. Okay, so what are one of the possible roadblocks? So to really generalize it fully, you can go to pointed closed convex sets. We don't have to require the set to be bounded. We can then show that easily that every pointed closed convex set is the intersection of all closed rational half spaces containing it. However, extending this theorem to any closed convex set is not possible, because you can have even a half space, closed half space, that's defined by a normal to that half space that contains at least 1 rational number and 1 irrational number. Then you see that there will be no way of representing that closed half space as intersection of rational half spaces containing it. The smallest rational half space that contains such a half space is the whole space. So you cannot go more general than that. And the main paper containing the result just appeared in Science Journal on Discrete Math. I hope that if you're interested, you'll take a look. And the little fact that I mentioned here with the roadblock to full generalization is in a little one-page note. So I would like to thank you very much for your patience, for sticking around. That's all I would like to say about the official part of the talk. But I hope that those of you who can stick around, we can talk more about these things at beer time. Thank you.
Well, thank you, Levent, for the nice talk. So any question from the audience, please unmute yourself and you can ask questions. Oh, okay. Henry has a question in the chat. It seems that TDI is closely related to obtaining a rank 1 optimal solution that guarantees solving the original hard problem. Does TDI gives a theorem like the Babinok-Pataki rank bounds? Can you improve the BP bound for this special case?
Very good question, Henry. Yes. So let me. Okay. So what do we do? So let's go back to the chain. I'm sorry, it's very small, but I hope you can see it. So for the primal restriction, we can have this integrality condition as the matrix X is rank 1. And that can formulate all kinds of difficult problems. Now, if you try to enforce exactly the same condition, if you say that the dual slack must also be rank 1, that is not the correct definition. You might say, how could you say a definition is not correct? It's a definition. The reason I say it's not correct is because it doesn't give you anything useful. For many interesting STP relaxations, if you require the dual slack to be rank 1 as well, it gives you infeasible problems here, useless thing that only. So for instance, let me just give you an example. If you applied it to the max cut, the famous max cut STP formulation that was used by Gömans and Williamson, what you get from here will give you something meaningful only when your graph is the complete graph and your weight function is represented by a rank 1 matrix. So it's extremely useless to require this to be rank 1. Another problem that you see is somehow related to your question, which is that when you have a relatively generic STP, you expect that strict complementarity should hold for it. I mean, it's not, of course, there are a lot of reasons when it shouldn't, but you should expect that it should. And if you have a rank 1 solution, which has a full dimensional normal cone, and if strict complementarity holds, then you would expect that the dual optimal solution will be rank n-1. So that's another reason why requiring the same rank 1 condition here is useless. So now coming back to the actual condition that we use, what we say is that instead of saying X is integer, we just say that X is sum of rank 1 matrices that obey this condition. And similarly, we say that S is summation of rank 1 matrices of this form, which obeys this condition with a minus sign. So in that case, indeed, there is a relation to how many rank 1 matrices might you have in that sum end. But notice that the matrices I am having in that sum end are all rank 1 matrices with a special structure, and I am enforcing coefficient 1 in summing those matrices up. So in that sense, it's not directly connected to the actual rank of the optimal solution here, because I'm talking about some kind of an integral decomposition of this matrix, where the integral is defined according to our definition. So the right analogy actually is, for those people who know, is the Hilbert basis analogy.
Okay, any other questions?
Yeah, I was wondering if you could go to the perfect graph page that you had there. These really nice results, Levent.
Thank you very much, Jim. You picked the perfect slide. Let's see where it is. Yeah, my eyes aren't very good. Please, okay, this one. Yes.
So I was wondering if you could just explain a little more about how your framework helps you with this second thing in the equivalence.
These guys.
No, so I mean, so you've got
these are old results.
These other equivalences, but if I just wanted to prove the second thing, a graph is perfect if and only if its complement is perfect. Am I to understand that this framework also helps you with a proof of that?
Oh, I see. I mean, excellent question. So for those of you who are not able to see, well, okay, so let me just say it quickly. What Jim is saying is that, so we have this theorem. We believe it's correct. But note that this theorem applies to all graphs. So if it applies to G, it also applies to complement of G. So which means that if I just take this statement and these statements, and then complement my graph and apply this part of the theorem, I should be able to prove also this between these two. The answer is yes. And I didn't check if it is trivial in this setup. But I will check and I'll report to you.
Okay, thanks.
I think that's an excellent question, because it does say that such a proof exists. The question is, can you just look at this STP and conclude in ways other than using Lovaas's replication lemma or something like that, for instance?
And I guess another sort of related question, what sort of certificates of non-perfection you get from your framework and how they relate to, well, so basically if somebody really wanted to get a shorter proof of the strong perfect graph.
I know where you're going. I know where you're going.
Say, what sort of certificates are you getting? Do you get any new certificates that are
excellent question. So before trying to answer your question, let me just say for everybody else, I mean, I love stating this theorem. Last time I taught CO 671, I stated this theorem. Of course, I included the strong perfect graph theorem in it. I stated it in 20 parts. I wrote 20 equivalent statements. So it is an incredibly nice theorem. So the certificates, the short answer is that I do not have anything new, because I mean, of course, I have a certificate, but again, let me go to my Mickey Mouse picture if it will help. Notice that, so we know that a given graph is not perfect if and only if the theta body is not polyhedral, right? Which then means that one kind of certificate relating to the theta body that's obtained in this space is that you think of this red convex set as theta body, it will have a nonlinear boundary, and it means that there is an objective function that you can pick that will certify, you know, non-polyhedrality. So of course, in that case, the set that we are dealing with here, which is the SDP formulation of the theta body, there is a corresponding objective function in the matrix space that will certify that the graph is not perfect. But that certificate is essentially trivially extending the certificate that we already have from Lovaas theta body, the corresponding linear function. So I do not have anything new, but what we have is, if you will, an equivalence class of certificates in that set, but it's trivial.
Thanks.
Does it answer the question, Jim?
Fully, yeah, thanks.
Thank you, great questions.
Okay, any other questions? Maybe I can ask a question from
yes,
people
please.
who haven't taken CO 650 like me. So I guess the machinery that you describe works if you have an SDP problem and then you lift it to a higher dimension and then you can use the chain. But in the situation that you can, in the DO, you can find some instance to make really, you know, all the steps of inequality become equation, and then you can prove something about equivalence or something. Is that how it works? And
very good question, Jane. Really excellent question. So when I say theorem proving machine, let me just say what you have to do. So maybe let me just go back to the linear programming one. So in the polyhedral case, proving, say, that the matching polytope is TDI. It's a theorem by itself, independent of the original TDI machinery. So you have some combinatorial problem like matching. You cook up some system of linear inequalities that you think exactly describe the convex hull of incidence vectors of your combinatorial set. Furthermore, you do think that that thing is TDI. So once you have done that, which is very hard work, if it is TDI, you just prove that it's TDI, and then you have the chain of inequalities becoming equations automatically. So in this new theory, the work is exactly the same. It's not different. So what I mean is that you have some formulation that's non-convex. You look at the STP relaxation. If you cooked up the right STP relaxation, then you just have to prove that that relaxation is TDI. That's all you have to do. Once you have proven that this relaxation is TDI according to our definition, you will have all of these inequalities become equations, and you'll automatically have a min-max theorem. But I'm not trying to minimize the task of, even if somebody gave you the right system of inequalities or the right STP, to prove that it's TDI is non-trivial. That's a theorem all by itself. But that's all you have to do in both the existing polyhedral theory from 1970s and in this new theory that I presented today. And what I'm claiming is that this theory is at least as rich as the original Edmonds-Giles theory, because I can embed, for 0-1 optimization problems. Does that answer your question?
Part of, but maybe I really was curious how this lifting thing. I thought when I was hearing the talk, I thought maybe it's a way to make TDI, but seems not.
No,
no,
no, it's not. I mean, there isn't. I have to tell the truth. I don't think there is a TDI fairy. There is. TDI-ness needs to be proven. So this is just a framework that you can crank with the right formulation, and a right formulation always exists. That's part of the theory. And once you find the right formulation, then you just crank this theory, and it will give you min-max theorems, and it will give you a corresponding non-convex dual.
Okay, thank you.
Thank you for the next question.
And yeah, any other questions from the audience? Okay, so let's thank Levent again for this such nice talk, and actually a nice lecture as well. Okay, so I think now we will start the grad house time. And I just want to mention again that from now on, we are going to separate the organization from the test seminar and the grad house meeting. And Shayla will be officially hosting the grad house time. So I'm just going to pass my host role to Shayla. So Levent, is this lifting thing a very, sorry, I shouldn't discuss seminar stuff, but I'm just curious, is it something like very standard approach where you have original STP? Like what's really the role that the lifting is playing here?
Okay, so there's something that was another, every thought colloquium that I was fortunate enough to give, I'm so grateful. One of the thought colloquia that I gave 22 years ago, I described the framework where any non-convex problem could be embedded as an STP with a rank constraint.
Okay.
So basically what they did is that took any non-convex set and wrote it as the intersection, as the solution set of a system of possibly infinite quadratic inequalities.
Okay, I see.
And then from that wrote a semi-definite programming problem with possibly infinitely many linear inequalities Together with the rank constraint, it could formulate any non-convex set.
Okay, I get it.
And any compact non-convex set. So that includes, of course, integer, finite integer programming, let's say. It also includes all kinds of continuous non-convex problems. Mm-hmm. So this kind of TDI-ness theory has a potential for going that far. Mm-hmm. But when we talk about this lifting, there is really nothing that special about that particular lifting. Mm-hmm. It's just an algebraic embedding.
I see.
So TDI-ness, even though we talk quite a bit about geometry, it's actually an algebraic concept. You have to fix an algebraic representation for your relaxation. In the case of polyhedral theory, it's very natural to pick systems of linear inequalities. But once you go to these the richer nonlinear settings, the number of choices increase tremendously. So the choice that I made is biased